Good afternoon, everyone. I'm Michelle Sanner, and today we are going to be learning a little bit about the different types of intermolecular forces that can occur within molecules. So by the end of the day, you'll be able to identify 3 types of intermolecular forces and what type of forces exist in that molecule based on the geometry of that molecule. So first, let's discuss what intermolecular forces are. So one of the ways that I abbreviate intermolecular forces is IMF. It's a lot quicker to write IMF than intermolecular force, but these are the forces that hold molecules to one another. And it's the very reason that condensed phases like liquids and solids can exist. Without intermolecular forces, all molecules would behave like gases that are just floating around in 3-dimensional space. But there's something about solids and liquids where the molecules are held more tightly together that enable solids and liquids to have those properties. And the forces that hold those molecules together are called intermolecular forces. They're different from bonds because they're just forces between 2 different molecules. If you think about international flying, it's when you fly from one country to another. So we're talking about a force that exists between one molecule and another molecule. They are far, far weaker than chemical bonds. Chemical bonds are much stronger than intermolecular forces. So those are the bonds hold an atom together into a molecule, but IMFs hold molecules together in their condensed phases, like gases, or like liquids and solids. The first type of intermolecular force I'd like to talk about is called London dispersion force. So London dispersion forces are the very weakest intermolecular forces, and they occur in every single molecule that there is. They, as you can imagine, electrons are in constant motion around the nucleus of an atom, and when their elements are bonding, those electrons are moving around constantly. At any given moment, there may be a greater concentration of electrons on one side than the other of a molecule, like here. And that creates something known as a momentary dipole. And a momentary dipole is not permanent. It's just a temporary moment at which there tends to be more negative things on this side of the molecule and more positive on this side of the molecule. So much like a regular dipole, except for the fact that this is instantaneous. It's just there for a moment. Because it's there for a moment, it's able to experience an attraction to the opposite charge of molecules nearby. So if this end is, again, slightly positive, and another nearby molecule also has a temporary dipole that's slightly negative, a small force is going to exist between these 2 molecules. And this is happening constantly and at great speeds and amongst billions and billions of molecules at a time. So because electrons are constantly moving, they can create temporary dipoles, even on non-polar molecules. So every type of molecule in the world experiences this London dispersion intermolecular force. And here's a little photo of it from our chemistry textbook, Davis, Fry, Sarquis, and Sarquis in 2009. London dispersion forces are present in all molecules, but they are the only type of intermolecular force that occurs in noble gases and in nonpolar molecules. So if you're given a problem that it asks you what type of intermolecular forces are present for a molecule, if it's nonpolar, your answer would be only London dispersion intermolecular forces. So let's look at the next one. The next type of intermolecular force is called a dipole-dipole force. And a dipole-dipole intermolecular force occurs where you have the negative end of a dipole, like right here, of a bond, attracted to the positive end of a nearby molecule that it is not bonded with. So in this example, I've got this green bonded to red, and of course it shares those electrons amongst itself, but it's also attracted to the nearby partially positive end of a different molecule. Likewise, its positive end is attracted to the nearby negative side of a different molecule, and so on and so forth. So these dipole forces, because they're permanent dipoles, they exist on polar molecules, these are much, much stronger. And you can see a sort of a pattern tends to form where these molecules are hold really closely together because of various different ways that they're attracted to one another. So dipole-dipole intermolecular forces occur in polar molecules where the negative dipole of one molecule is attracted to the positive dipole of another different molecule. These IMFs only occur in polar molecules that contain dipoles. So if you're given a problem and they ask for what type of intermolecular forces occur in a given substance, well, you want to check and see if it's polar or nonpolar. If it's polar, it includes both London dispersion and now dipole-dipole forces. The other thing I should mention about dipole-dipole forces is that they are significantly stronger than those London dispersion forces. It's much, much harder to pull those molecules apart from one another. So like I was saying, polar molecules have both the dipole-dipole interaction and the London dispersion force. So there's another type of intermolecular force that we're going to study this year called hydrogen bonding. And it's a bit of a misnomer because this is an intermolecular force, not a bond, but it does result from the presence of a hydrogen bond. So hydrogen bonding is a special type of intermolecular force that occurs when you have hydrogen bonded to a highly electronegative element like fluorine, oxygen, or nitrogen. So whenever you see hydrogen bonded to oxygen or hydrogen bonded to fluorine or hydrogen bonded to nitrogen, you have an extremely strong dipole that we call a hydrogen bond. So this very, very strong dipole are able to attract the opposing dipole end of nearby molecules. So H bonding tends to be the strongest of the intermolecular forces. Let's look at how this works. Well, here is less electronegative hydrogen. Because it's less electronegative, it is not as good of an ability to attract electrons to itself. So its end is partially positive. Oxygen, on the other hand, highly electronegative element, it is partially negative on this pole. This partial negative side can attract to the hydrogen-facing side of a nearby water molecule. Likewise over here, this partially negative side can be attracted to the partially positive side of this hydrogen molecule. And in turn, these hydrogen sides are attracted to the oxygen sides of nearby molecules. And so you have this kind of growing lattice, this growing network of connections on all ends of water, causing it to be very strongly attracted to other water molecules. And this accounts for many of the different properties of water that we'll discuss a little bit later. So hydrogen bonding is the strongest of all the intermolecular forces. And again, it only occurs when you experience hydrogen bonded to one of these highly electronegative elements, F, O, or N. I like to think of it as hydrogen bonding is fun, not quite fun, but fun. Here's another way of looking at hydrogen bonding. So as you know, that oxygen has two unpaired electrons not participating in bonds on this slightly negative end. Those unpaired electrons are very much attracted to slightly positive hydrogen in nearby molecules. So just a different way of visualizing what's going on between electrons and the slightly positive ends of the other dipoles nearby. So a hydrogen atom is partially positive and attracted to non-bonding electrons here in a nearby molecule. Like I was saying earlier, hydrogen bonding is not a bond, but it is rather an intermolecular force that involves a hydrogen bond in the molecular structure. And molecules with hydrogen bonds end up having all three types of intermolecular forces. They have the London dispersion forces that are present in every molecule. They have the dipole-dipole forces that are present in all polar molecules. And they have the very strong hydrogen bond intermolecular force as well. So when you see an element that has H bonded to F, H bonded to O, or H bonded to N, great example of something that has all three of these types of intermolecular forces. So let's recap. Relative strength. You know, how strong are these intermolecular attractions when you compare them to one another? Well, London dispersion is your weakest. Dipole-dipole forces are stronger. They are a stronger force. And hydrogen bonding is the strongest type of intermolecular force. All of these types of intermolecular forces are far weaker than chemical bonding. It doesn't take a tremendous amount of energy to separate a solid, but it does take a tremendous amount of energy to separate a bond. So all of these intermolecular forces, much, much weaker than chemical bonds. So we're talking about something completely different than chemical bonding now. So how do we determine what types of intermolecular forces are occurring in a molecule? So given that you will get a chemical formula, start by drawing the Lewis structure of that chemical formula, obeying the octet rule, following the formal charge convention if necessary, and drawing a clean and quality Lewis structure. Remember, all the molecules have London dispersion forces, so you can assume that this molecule will have London dispersion forces. Next, identify the geometry based on the central atom of the chemical that you're trying to solve. Draw any bond dipoles if they exist, and molecular dipoles, and if that chemical is polar, then you can also include dipole-dipole intermolecular forces. So once you've determined molecular polarity, you'll be able to decide if this is a polar molecule or a non-polar molecule. If it's polar, don't forget to include the dipole-dipole intermolecular forces. Lastly, look for any hydrogens bonded to highly electronegative elements like F, O, or N, fluorine, oxygen, or nitrogen. If hydrogen is bonded to one of those three, you can also include the hydrogen bonding intermolecular forces as well. So let's use this procedure to actually start drawing Lewis structures, start making some predictions about the intermolecular forces that are present in a couple different types of molecules. All right, let's start with this first molecule. I have phosphorus bonded to 3 fluorines. My phosphorus has 1, 2, 3, 4, 5 valence electrons, and each fluorine has 7. Starting at the top and moving clockwise, I'll begin making pairs here. So after I've drawn the Lewis structure and cleaned it up a little bit, I can identify the bonding and non-bonding regions of this central atom, in which case the central atom is phosphorus. So here's a good Lewis structure. All of the octets are full in every single element. So looking here at the central atoms, I'm identifying the number of bonding regions of electron density and the number of non-bonding regions of electron density. I like to think of this to kind of simplify. How many sides of is phosphorus touching something in bonds? So it looks like we have 1, 2, 3 bonding regions. And how many sides are touching non-bonding electrons? 1 non-bonding region. So this shape is this is one of our examples. Remember, everything's polar unless it satisfies some very unique conditions. To be nonpolar, you have to be linear, tetrahedral, or trigonal planar and have the symmetry around the molecules on the outside. In this case, I don't have that symmetry. So this is an overall polar molecule. It's a trigonal pyramidal molecule, according to our Vesper theory, which you can always go back and review. And because it's a polar molecule, I can say that it has the following intermolecular forces. It's going to have London dispersion forces, because every molecule includes London dispersion forces. And since it's polar, it's also going to have dipole-dipole forces. And then my last question is, does it have H bonding? Well, I don't see any hydrogens bonded to highly electronegative elements. So no, this one does not have hydrogen bonding. So the answer to this question is, what types of intermolecular forces are present in PF3? London dispersion and dipole-dipole. So now try pausing the video and doing this next one on your own. Remember, here we're going to have carbon will be the central atom, so that's the one that you're going to check geometry on. See if you can draw the Lewis structure here. Pause the video, identify its polarity, and come up with a decision. What type of intermolecular forces are present? Okay, let's see how you did on the Lewis structure. I have carbon in the center, double bonded to oxygen, which has 2 lone pairs of electrons. Carbon single bonded to hydrogen twice. And I've drawn the dipole, the individual bond dipoles here. So more electronegative oxygen has the dipole pointing towards that. Between carbon and hydrogen, the more electronegative element is in fact carbon. So overall, my dipole is pointing in this direction. So it is thus a polar molecule. Looking at geometry, I see that I have 3 bonding regions, that is to say 3 areas of electron density touching bonds, 0 areas of electron density around carbon. So there are no non-bonding electrons here. So now I can determine the types of intermolecular forces. Well, all molecules include London dispersion forces. Polar molecules, such as this one, include dipole-dipole forces. And all that I'm left to decide is whether or not this also includes hydrogen bonding. I do see that there is a hydrogen bonded to carbon right here. However, carbon's not electronegative enough for this to include hydrogen bonding. So remember, for something to have hydrogen bonding, you need to have H bonded to F, O, or N. So in this case, we are done. London dispersion and dipole-dipole are the only types of intermolecular forces that occur in this molecule. Let's do one more together. Identify all the types of intermolecular forces present in the following molecule. Try to pause the video and see if you can identify all of the IMFs present. Okay, let's see how you did. So this is a really easy one because it's just a linear 2-atom molecule. You have hydrogen bonded to fluorine, which has 7 valence electrons. This forms a single bond. The overall bond dipole is the same as the molecular dipole, since there's only 1 bond in this molecule, and it's pointing towards fluorine. So this linear polar molecule certainly includes our London dispersion, it also includes, because it's polar, a dipole-dipole force when it interacts with other molecules that are the same. Its hydrogen will be attracted to nearby fluorines, and the fluorines will be attracted to nearby hydrogens. And then finally, we decide, is this a hydrogen bond as well? So we're looking for H bonded to F, H bonded to O, or H bonded to N. And indeed, we have H bonded to F. So this molecule would also experience the intermolecular force of hydrogen bonding. And so that's how you determine the types of intermolecular forces that are present in a given molecule. So you work your way from the chemical structure into the Lewis structure, from the Lewis structure to the geometry, use geometry to determine polarity, and use that to decide what kind of intermolecular forces occur. What we'll be learning next is how to take intermolecular forces and identify different properties of these substances based on their chemical structure. Intermolecular forces do affect many physical properties of matter, but we'll talk about those another day. I hope you're doing well and have a great day.